Hello everyone, this is Scott from Pyvot, and I want to share some application data regarding separation of peptides and proteins. I'm going to jump right into this presentation, and I look forward to hearing your thoughts as well regarding this. So here's a list of phases for separation of high molecular weight compounds. This is a pretty detailed table. It has various phases. Everything including C4, C8, as well as C18. And we will highlight these in more detail as we go through this. The particle size for most of them, since it is a core shell particle, is 2.6 micron, but we also have a 3.4 micron as well, which we'll highlight going forward too. The pore diameter ranges between 16 nanometers and 100 nanometers, or 160 angstrom and 1000 angstroms. And for those interested, the pore size distribution of the core shell particle is noted here. And again, we're using nanometers to show this. Now, what is HFC-18? And so this is a Hexa-Functional C18, and it has 6 functional groups. This is a unique technology to Chromanik that complements the sunniest bonding technology, or the trifunctional bonding technology. So this 6 functional group phase is much more stable under acidic conditions. So let's highlight this a little more. So for example, the stability of HFC-18 under LCMS mobile phase condition is something like this. And so we are using 0.1% formic acid, the pH of 2.6, 70 degrees Celsius. If you look at the time of 1,000 hours, this is really stable, and we're using a 2.1 millimeter ID, 50 millimeter length column. You can see that the relative retention percentage is above the 95% line as well. So how does this all work here? And let's look at some comparison data as well. And something to note, here's the Sunshell C18 wide pore column. You can see this is a 16 nanometers as well. This wide pore column is actually very stable. It's actually more stable because the ligand density, or the carbon loading, is twice that of the HFC-18 column. But we just wanted to show you some differences in separation. So there's some, the separation of the peptide is different. We're using a sample of tryptic digest of myoglobin. Just something to look at to give you some perspective. We'll go look at a second comparison as well, and this is for peptides, or the second example, and this is a sample using tryptic digest of cytochrome C. And we're using a similar separation condition. The mobile phase here, 0.1% TFA and acetonitrile and water. And you'll see that the separations are a little different. And just to give you some more perspective as well. And we're using a gradient program here as well. Now, what about separation of proteins in relation to effects on temperature? You can see this here. We broke it down to 25 degrees, 60 degrees, and 80 degrees Celsius. We're looking at 5 different samples, or protein samples as well. And basically what this slide is saying, the higher the temperature, the better the separation. Now, taking the same separation condition and looking at effect of gradient time. And what you'll see here, and we're looking at the same samples of protein, you can see that the longer the gradient time, the better the separation. Now going down, we're going to look at separation of proteins, looking at different columns that we had highlighted here. And we'll look at separation of proteins in 5 minutes. Then we'll look at separation of proteins in 60 minutes. And if you look at this table, you can highlight, you can see the C830 high throughput column. And remember, this has a 3.4 micron particle size. And this shows a smaller peak width for each protein. And so basically the Sunshell C30 high throughput option has thin porous layer, which is only 0.2 micron, while the others have 0.5 micron of a porous layer. So basically the mass transfer is done earlier in the pore of the 0.2 in the 3.4 micron, and then in the porous layer of the others is 0.5. So that's what gives it its advantage, particularly in 5 minutes compared to the others. Now, what about in 60 minutes, separation of proteins in 60 minutes? Something to look here, the injection volume in this case is 1 microliter. And so the C4-100 and C8-100 showed a sharper peak. But when going back to the C830 high throughput column, when you use less of an injection volume, in this case 0.5 microliters, it holds up quite well and has similar peak width to that of the C8-100. So just to give you some different perspective in the separation. I want to highlight one more slide here, and this is the separation of monoclonal antibodies. And this is again purified from cell culture using protein G. And we're looking at different phases. So we have a core shell C8, and this did not elute very well. And then looking at both a porous and a core shell column with a 300 angstrom. The best separation was with the Sunshell C4-100. And again, this is 100 nanometers or 1000 angstrom, just to give you some perspective. This is all I have for now, but I look forward to hearing from you. If you have any questions, please click on the links on this page as well, and we look forward to hearing from you. Thank you so much.